these are the three factors that the three major factors that will determine or will cause a substance to be solid, liquid, or gas.
Right.
You need to remember that solids are the most highly structured.
Right.
Okay? And so the more all of these factors impact some substance, the particles in a substance, whatever those structural particles are, the more likely something is to be a solid.
Right.
And the less these factors impact the behavior of those structural particles, the more likely that substance is to be a gas.
Yeah.
And then liquids are the intermediate state, but liquids can only occur when there is outside pressure on a substance.
Right.
So, for example, there is no liquid in space because there's virtually no pressure in space. Okay?
What about people who say there's water on Mars or whatever?
Well, Mars has a significant amount of gravity, but it has a very weak, very slight amount of, much smaller amount of a atmosphere than the Earth does. So the pressure there is much lower. But there still could be enough pressure for liquid water to occur. I don't know. That's outside my area. But there certainly could be frozen water, because water can be frozen, or it can be gas in space, or even in low pressures. Yeah.
I was watching Discovery Channel one time, and they said that there's water on Saturn's moon, or is it Jupiter's?
One of Jupiter's moons, it has a frozen surface and is believed to have basically a water ocean underneath that frozen surface. I don't know that.
Oh, you don't know?
No.
I'll go look it up. And
I know that Venus has. Is it Venus?
Could
Mercury,
be.
Venus.
Venus is the hot planet. That's
the sister planet.
Yeah.
Venus has clouds of sulfuric acid.
Dude, that's crazy. Like, if you went on there, you'd burn up.
Well, kinda.
Well, not.
Yes.
If you poured a bunch of water out into space, would it go into gas or like?
Oh, that's a really good question. Did y'all hear the question? See, it helps when you pay attention.
I was paying attention, Mr. Tedder.
Pour water out of space.
Well, first of all, if you tried to pour water out into space, it wouldn't pour, because it's going to almost immediately. I mean, it's really, really fast. It becomes either solid or gas, depending on the temperature where you are. So, and the really strange thing about that is everything has to do with, if you're close to the Earth anyway, whether you're in the shadow or in the sunlight. So if you're in the space shuttle, and on the sunlight side of the space shuttle, it becomes a gas. If you're on the opposite side of the space shuttle, a very good chance it's going to become
solid.
It's going to ice. It's going to ice. Yeah. Okay. Now you're really talking about something that I haven't looked at a lot. So, don't hold me to that, but that's the basic idea, okay?
How do you drink water in space?
You have to have water pressurized. I mean, the spacesuits are pressurized. There's air pressure inside the space shuttle, so there's liquid water inside.
Oh,
yeah. It's just if they went outside in the space for like a picnic, they wouldn't be able to drink
that's
water.
a good question.
What?
Does it affect the water in your body?
Absolutely. What I've heard is that if, say, you were to be thrown outside the space shuttle, like just thrown out. It's my understanding that you have about 9 seconds before the liquids start to boil out of your body violently.
Oh,
That's pretty freaky.
Yeah, pretty freaky. Okay.
Make sure you wear your swim trunks.
Well, you actually do a little bit of both, because the liquids that are able to get out will vaporize, but the liquids that are sort of trapped inside, then they tend to freeze. So yeah, it's a pretty nasty way to go. All right. So then, we also have this factor we call that temporary dipolar. This is when you have nonpolar substances, or you have locations on molecules that are nonpolar. So you can have a combination of polar and nonpolar. Alcohols are like that. They have nonpolar ends and they have polar ends. Well, on the nonpolar ends, or on a nonpolar molecule, this temporary shift in electron density is what causes a temporary dipole and allows these particles to have some stickiness. You want to stick together and form liquids or form solids. Okay? All these things play together. They come together to make solids, liquids, or gases.
Uh-huh.
Okay, so almost anytime you have a covalent network structure, like a diamond, like glass, there's some other crystals, but those are the two that you probably are most familiar with, they're going to be solids. They have, at least at room temperature pressure, I mean, even in space, they're going to be solids. Okay? They have so much attraction, so much is holding them together, so much structural integrity, they almost have to be a solid. You have to really, really heat those up to get them to be a liquid. Okay? All right.
Yep.
Metals, they have that electron C model. Okay, where you have the particles sort of glued together with the electrons that are being shared all through the structure. All right? That creates a wide range of melting and boiling temperatures. Okay? But on the whole, they have just somewhat less of particle integrity or particle strength, the attraction between those particles to hold them together. So if you averaged everything out, they would rank just under the covalent network structures. Okay, and then the ionic particles. And again, the ionic particles have a pretty wide range, but those oppositely charged particles, positive particles and negative particles, and they can be different charges. It doesn't have to be 1 plus and 1 negative. It can be 3 plus and 1 negative. Okay, but those opposite charges create a very strong attraction. So almost all of those three kinds of structures, covalent network, metallic, and ionic, are almost always going to be a solid at room temperature and pressure. Okay?
Yeah.
So lab temperature pressure, those are solids. Now the exception, of course, about metals that you know about is mercury, which is a liquid metal at room temperature and pressure.
Right.
All right. But then once we get outside of that, then we get down into polar substances. Now we start looking at the size of the particles and the amount of polarity on that structure as determining whether that's going to be a solid or a liquid or a gas. So I could have a non-polar structure that's made of nothing but a carbon chain, you know, CH3, CH2, CH2, and on and on.
Shout out to Misha.
Okay. If I get a chain that's like 20 carbons long, okay, that's asphalt. That's a solid, and there's no polarity on there. But the length and shape of that molecule is long enough that we've got lots of places along here for that temporary polarity, that temporary shift in electron density to occur, and where that occurs, there then is stickiness between those molecules. So those molecules can be drawn together wherever those shifts in electron density occur in the same region. So if there's a region right here where this side has a partially negative and a partially positive over here, then there's attraction between them at that point. Okay, so the larger the molecule, even for nonpolar molecules, the more likely you're going to have them drawn together into some kind of structural form that you can identify.
When they go apart, if it was two negatives, partially negative.
This is a positive here, I'm sorry. I just didn't write it very clearly.
That's
Okay?
all right. That's all right.
So wait, how long is the temporary dipole? Like seconds wise? Or minutes?
Seconds wise, nanoseconds wise. Really, really temporary. But the shift occurs often enough
Like that?
that it's continuously occurring along that structure. Okay?
Right.
All right. So there's some opposition and some attraction, but overall, because of the length, you get enough attraction that they tend to stick together. And so this is what we make. Something that's really, really long, made of a carbon chain, tends to be asphalt. Okay? When we take crude oil, comes out of the ground, we go and put it into a cracking tower that separates all the different carbon chain lengths. What they do is they take out of the bottom. If you could say shovel out of the bottom the asphalt.
Nice.
Okay, and what comes out of the top is methane, and then in between you got aircraft fuel and gasoline and kerosene and all those things. Okay, lubricating oils and things like that are down near the bottom somewhere. Okay, all right. Then if we have a carbon chain, for example, and remember carbon chains are nonpolar, all right? We could draw the structures out and see that, but it gets pretty complex. Just try to remember methane. If we do the structure of methane, that's supposed to be a triangle.
It's all right. We'll forgive you, man.
I appreciate it.
Yep.
Okay? These are all slightly polar bonds. These are all slightly polar bonds here, but they're all equally spaced around that central carbon,
You're right. You're right.
so that the overall effect is a nonpolar molecule. Well, when we get a carbon chain, those carbons are also surrounded by hydrogens in such a way that you pretty much have a nonpolar molecule because of the same effect. And we don't get into the structure in this class of how they arrange themselves so that, for the most part, if you did the math, in three-dimensional geometry, you would actually have all of those bonds equally spaced around those carbons in that chain. Okay, but it does. Just take my word for it because I don't want to get too complex here.
We take your word, man.
All right. Well, if we have a carbon chain then, so a carbon chain like this is nonpolar. But I can stick a polar section on there and something strange happens, okay? You have a polar end, a nonpolar end, and a polar end. This end up here, this O to H, and the two lone pairs that are sitting up here, okay? That's a very polar structure right there. That's like water, remember, is H, O, H with those two sets of lone pairs up there, okay? And it's a very polar molecule, so this structure is very polar. All right? If I have a structure like this alcohol has a lot of polar attraction to the next alcohol. What is so funny? Really, what's so funny? What did I do?
No,
Help me out here.
No, nothing. No.
So y'all aren't laughing at something I did?
No, sir.
What are you laughing at?
We're just having a good time.
Yeah, but what are you laughing at?
Nothing.
All right. Listen, if you can't share it with me, don't do it.
Okay, yes,
Okay?
sir.
All right.
Sorry.
Okay.
Got something?
All right.
Yeah.
So then the kind of questions that can be asked are like those on the practice test. How do you compare these things? All right. If I had
You know what I like about this class, Mr. Tedder?
what's that?
We learned a lot more than chemistry. Like just a second ago, I learned
Well,
more.
I'm trying to relate all these other things to chemistry.
It's awesome. It's like little fun facts. That's a lot of letters.
Okay. So if you'll write that down in your notes.
Oh, we get a handy dandy writing utensil out. May take an hour.
Now this is an individual thing for you to do. Okay? Not a group thing. Not a paired thing, but an individual thing to do. I want you to rank these. I want you to rank these in this manner. Which of these particles is most likely to be a solid? 2, which one is most likely to be a gas at room temperature and pressure? Which of these particles has the most likelihood of being let's don't say solid, let's say a liquid. And which has the most likelihood of being a gas? And rank all of them in that order. Okay, yes? Yes. Okay. Which of these has the most likelihood that it's going to be a liquid, and which of these has the least likelihood it's going to be a liquid, that it'll be a gas instead, and rank them in order. Okay? And then I want you to write an explanation, a detailed explanation of how you know that, or why you think that. Okay?
So would one be most likely to be a solid or a liquid? Or
Mhm.
would one be most likely to be gas?
Doesn't matter how. Just you can do a grid if you want to that shows. You know, rank them in here.
All right.
Okay, if you want to do it that way. Okay, and all of these are at room temperature
And pressure.
and pressure.
Okay.
Okay.
All right.